What do you want to talk about? Massive amplitudes. All right. So who wants to vote for massive amplitudes? Yes. Yes. All right. Now I can have coffee. You can start. Okay. Fine. Okay. Massive amplitudes. It is. Let me. Okay. Well. I may occasionally need a formula or two from our paper, so you can, if you can pull it up on your laptop. If I need one, maybe I'll just come look at it. But I think we'll be okay for a while. See if I can. Yeah, I think we'll be okay for a while. Okay, so all right. I'm so glad you guys want to hear about massive amplitudes. That's great. So we'll do massive amplitudes with any spin. How many of you, how many of you have looked at my paper with the Wangs? Okay. How many of you haven't? No, I didn't. I mean, no, I'm not taking notes. Oh, okay. Good. That number went up significantly after that. Okay. Okay. So let me give a. Okay. Actually, maybe I just have a better idea. Of those of you who've read the paper, how many know right now or remember what the massive spinor helicity business actually is and what it looks like? Okay. And how many people remember the derivation of the Compton amplitude, for example? Okay, good. So we can talk, and the Higgs mechanism, probably nobody, right? Okay, good. Okay, fine. So that gives me an idea of what we can do. Okay, very, very good. So, all right. So let me. I want to assume that you've around half of you haven't seen the paper. So I will start. I will start from the beginning, but it doesn't take long to get up to speed. So let me remind you of the. So there's just some kinematical problem here that we want to solve first, and it's a very basic kinematical problem, but it's a kinematical problem that really goes to the heart of what's new about the on-shell approach to thinking about scattering amplitudes. And the kinematical problem is simply this, that amplitudes are not Lorentz tensors, right? Amplitudes are, when we talk about massless particles, they're labeled by helicities. So one way of doing it is by labeling, oh, this chalk is crap. What happened? Huh?
Did you get a wet one?
No, it's not a, really? But, oh, that one's better, okay. What do you mean a wet one? I mean,
No, it's on this over here.
how strange. All right, let's put it over here. Okay. So we have amplitudes labeled by helicities and momenta, and the real symmetry transformation properties of amplitudes. So first, by translational invariance, there's a delta function for momentum conservation. That part's easy. But the question is how it should transform under Lorentz transformations. And the real transformation properties of amplitudes are, for example, if we have massless particles, it should have the property that when you Lorentz transform the momenta, you should pick up the little group phases, or the product over A, e to the I h a p a, of m h1 hn of the piece. Okay, so this is the fundamental transformation properties of scattering amplitudes. And if you remember the story of the whole story of the little group, has everything to do with the fact that if we want to just label particle states. So I'm sort of copying the notation that, for example, Weinberg uses in this description. So if you have particles of, if we have some particle state, we're labeling it by momentum and any other indices that it might carry. We would like to figure out how Lorentz transformations act on this. Okay, so we want to find for any Lorentz transformation lambda, we want to find how u of lambda acts on the state. And the most naive thing that this does is just Lorentz transform the momentum. Okay, but this is too naive. In fact, this is what you'd get if the particle was a scalar and the sigmas were just some internal indices, global symmetries, whatever. Okay, but it's not the most general transformation property you could have. So this is not true in general. And you know that it can't be true for particles with spin, right? Because in the most basic case, let's say you have a massless particle moving in the z direction. If you do a Lorentz transformation that's just a rotation around the z-axis, then it doesn't change the momentum, but certainly you should pick up a phase, right? That corresponds to the spin of the particle in the z direction. So we know there has to be something here that knows about the spin of the particle or the helicity of the particle. And the question is what it has to be in general. And Wigner's answer to this question was to just be careful about talking about what the states are to begin with. So he said, let's take some reference momentum k mu and talk about a state labeled by k and sigma. Then he says, for any other momentum p mu, let's write it as some L that depends on P on K, a Lorentz transformation L on K. Now notice that this L is not unique, right? So I'm making a choice. I pick one way of doing it, so pick one. So we make a choice for what the L of P is. Again, obviously it's not unique because when I'm done, if it's moving the z-axis, I can just do any rotation around the z-axis, and it doesn't change. So I have to pick one. Okay? But having picked it, I now define. This is very important. This is a definition. I define P to be u of L of P acting on K and sigma. Okay? And now I'm done defining the states. Okay? So now I can ask the question, how does a Lorentz transformation act on u, on P and sigma? And well, again, naively, it's lambda P. But let's see how this should arise. So this is u of lambda, u of L of P on K and sigma. And clearly, no, that's the point. This is the definition. That's how that's what I'm. This is what I'm using to define what I mean by the labels here and there. Okay. In general, if I had something else, I would just absorb that in the rotation on what I meant by sigma on both sides. Okay. So for one momentum with this choice, you can take that as a definition. But now I'm stuck, right? Because now when I do the transformation, it's exactly what you're saying. It's not obvious, and that index could actually change and will change in general. Okay. So if we just, and that's exactly what we do here. So this is u. I mean, clearly we want to get something like. We want u of L of lambda P times u of L of lambda P inverse lambda L of P on K and sigma. Okay, so I just added a u inverse. Okay, and I move that one on the inside. Okay, and so that's great. This is L of lambda P on something. Now notice that this whole guy, you can call it W, that depends on lambda and P, and L implicitly, of course. But W has the important property that W on K is equal to K. W K mu is equal to K mu, right? because W takes K. L sends K to P, to lambda P, and then this sends it back to K. All right? So this is some W such that WK is equal to K. Now that's the famous little group. And so what I learn is that this thing, whatever it is, sends K back to itself. But in general, this part could equal some d sigma sigma prime that could depend on W times K and sigma prime. Okay, where that d is just a representation of the little group. Okay? And so I'm done. I learned that U of lambda on P and sigma is in general this d sigma sigma prime that depends on W, that implicitly depends on lambda and P, times P again with sigma prime. Okay? So that's what we wanted to see, is that, lambda P. Okay, so we get a Lorentz transformation together with a little group transformation on the sigma index. Okay, so that's why the sigma indices are representations of the little group. And now what the little group is depends on whether the particle is null, is massless or massive. When the particle is massive, the little group is trivially just rotations, because you can go to a frame, you can choose k mu, so k is a particle at rest, and so the little group transformations are just ordinary rotations. The analog of that when the particle is massless is a little more interesting. There's no difference in the number of generators of the little group in the two cases, right? One nice way of thinking about what the massless little group is like if you boost the massive one. So if you literally take a linear combination of the generators that start off at rest as just being the rotation generators, and you boost them, then the algebra is exactly the same. You know, in 3 dimensions it would just be SO3. But the coefficient of two of the generators is getting smaller and smaller, or larger and larger, depending on how you scale things. The way you can think about it is that SO3 is like the symmetries of the sphere, right? Surface of a sphere. And what you're getting here is like blowing up the sphere, so the radius of curvature is going to infinity as you boost the particle. But you're always imagining being in the neighborhood of the North Pole. So in the limit, what does the symmetries of the sphere turn into? It turns into the symmetries of the plane, right? So as the particle becomes massive, the symmetry is no longer SO3. It's the symmetries of the Euclidean plane, which is the same number, right? I have the rotation and 2 translations in the x and the y directions, okay, instead of the 3-dimensional rotations of a sphere. So the little group for massless particles, if I'm in 3 dimensions, the little group for massless particles has 3 generators, Tx, Ty, and Jz, if the particle is moving in the z direction. Tx and Ty is a particular linear combination of Jx, Jy, and the boosts in the x and y directions, okay? Such that the commutation relations are just Tx and Ty is 0, and Tx and Jz is Ty, and Ty and Jz is minus Tx. I'm not putting in the i's, okay? But this is exactly the symmetries of the plane. So just translations in the x and the y directions and rotations around z, okay? So, and what I was mentioning is that you can think of this as just like Galileo is related to Lorentz by a contraction. This is exactly the same, okay? If you actually got it from the boost of a massive particle, you would have on the right-hand side here, you would have some epsilon Jz, okay? And so if you rescale Tx and Ty by a factor of 1/root epsilon, you go back to the normal SO3 commutation relations. Okay? But in the limit, as you send the boost to infinity, the particle becomes massive, this thing really goes to 0 and you can't scale it away. So it's really just like Galileo and Lorentz Lorentz contracts the Galileo. Similarly, the little group for massive particle boosts it to infinite boost where it becomes massless, contracts to the symmetries of the Euclidean plane. So, and here comes the final argument that that if I want to label a generic state here, because Tx and Ty commute, I can just give eigenvalues for Tx and Ty, whatever I want. But if those eigenvalues are not 0, then I can do rotations to get an infinite number, continuous infinity of degenerate states. They're all massless. And so a generic representation has a continuous infinity of states. And so the usual argument of the textbooks is that that's unphysical and we should throw that out. That's not a very good argument. Okay? But anyway, it's a typical argument people make. And we certainly don't see them in nature, as far as we know. So in order to avoid that strange infinity, you have to actually say that the eigenvalues of Tx and Ty are 0. And then when you make them 0, now the states are just labeled by helicity, just Jz. So that's this reduction of the number of degrees of freedom that we're talking about is seen in this sort of simple group theoretic way. Anyway, in general, yes?
This is an SO3 group, right?
No, it's now not SO3 anymore. In this limit, it's called E2. It's the symmetries of the Euclidean plane.
Why isn't it E3?
It has 3 generators, so it's the same. It has the same number of generators as SO3. Okay, so that's why I described it this way. I mean, we could just sit there and figure out the generators and just do the exercise of seeing what linear combination of the generators of the Lorentz group annihilates a null momentum. Okay, and it's not so hard to do that way. But I wanted to do it this way to give some more intuition of how it's connected to the massive case. And it's connected to the massive case by taking the SO3 generators, taking 2 of them, x and y, the ones that are not in the direction of the boost, and making their coefficients. Making the coefficient of the right-hand side of their commutation relations smaller and smaller. Okay? At any finite value, simply by rescaling them, you go back to SO3. Okay? But literally in the limit where they become massless, which corresponds to take that parameter to 0, you can't do that, and it just becomes the Euclidean plane. But it's not as discontinuous as it sounds, because it's just like a sphere blowing up. Okay? So if you look at the symmetries of the sphere blowing up, and you're somewhere in the neighborhood of the North Pole, in the limit where it becomes infinitely big, you don't see the curvature anymore, right? And so it's just the symmetries of the plane.
So
Okay?
there are no Euclidean motions or anything, it's just the rotational symmetry.
It's just a rotational symmetry of the sphere, and the limit of the sphere becomes infinitely large. Okay? And the limit as the sphere becomes infinitely large, that those symmetries are the same as that of the 2-dimensional plane.
Yeah, got it. Thank you.
Okay?
Do you find the argument to excluding the continuous spin particles convincing?
No, not at all.
Okay.
Not at all. And various people have written papers over the years trying to think about them. It should be excluded or not with deeper amplitudes-based reasons. So, something that will be great is if you could prove that no such amplitude involving these particles could factorize properly, or, we have similar things that exclude other funny things like massless higher spin particles. There are things that look more normal we exclude in a more convincing way without these arguments. This subject is still kind of in a bit of a shambles. I think the sort of best papers in the last 4 or 5 years were written by Toro and Schuster, with some more recent ones that are kind of pretty nice, but it's still not. No one has written down consistently factorizing 4-particle amplitude, for example. And part of the problem is that the 3-particle amplitudes are weird enough that it's not clear what the rules should even be. Anyway, I encourage you to look at the papers. Oh, you already looked at them. Okay. Okay, then, yeah. But no, I definitely don't find the arguments in the literature convincing. Yeah.
There's also another one about the coupling of states with a thermal bath.
That's also not very convincing at all. Yeah. That, this is not some weird, it's something that's very basically tied to the symmetries of space-time. If there's a reason why it's, it can't have a dumb reason why it's wrong. It has to have a better reason than those why it's wrong. And you can come up with a huge number of reasons why all those arguments are just crap. You have infinitely many states, but you can have weak coupling. It's not obvious you would thermalize all of them. There's like, when you have a hot plate, literally, when you have a hot plate, coupled to like a plate in the third dimension, there's also infinitely many modes of the particle in a box in the whole room that couple to the plate. It doesn't mean the thermodynamics of the plate doesn't make any sense. And that's because there's a hierarchy in coupling strengths of all these modes to the plate. So before talking about interactions, just at some blah blah level, you can't rule these things out. Otherwise, you'd also say literal plates are illegal, right? Which is ridiculous. So just the presence of an infinitely many modes doesn't make a literal plate illegal. So I don't think any of those arguments are particularly convincing. Yes?
Do you have a good argument for why origin?
Sorry?
Do you have a good argument for why you're at the origin or not?
I think the only good argument is we haven't seen these guys. It's not and because they're massless, they should have been easy to see. So that's the only good. So if they exist and they're not inconsistent, then they're incredibly weakly coupled and they're not super obviously relevant to the world. They have to be massless, right? So that's that's a perfectly fine reason. But trying to say there's something deeply theoretically wrong with them at these very general levels about free energies and thermodynamics and stuff, I don't think is remotely convincing. I'm very skeptical that they make sense, but I'm not swayed by those arguments yet. Anyway, okay. So once we do that, in general d dimensions, the little groups are in d space-time dimensions. For massive particles, the little group is SO d minus 1. And for massless particles, it's SO d minus 2, because we have to go down to this origin, and so we have one fewer rotation generator that we can talk about. Okay? And so, from 2 points of view then, life in 4 dimensions is awesome. Because life in 4 dimensions is the case where both of these groups are as simple as possible without being too stupid and boring. Okay? So if we're in, for example, 3 space-time dimensions, then for massive particles already, they're just labeled by SO2, right? And massless particles, what does it mean? By the way, what does this mean? So what does this mean about life in 3 dimensions? That it's labeled by SO1. Huh? That's right, it's D2. So that means in 3 space-time dimensions, there's no such thing as photons or gravitons, gluons. All you can have are bosons or fermions. Okay? So because all that can happen is that you pick up a minus sign or not. Okay? So there's no such thing as helicity. Okay? And in fact, for massive particles, all you have is the analog of helicity, spin. Okay? So that immediately explains all kinds of things. Why are there all these fancy dualities in 3 dimensions? Polyakov said that photons can be Goldstone bosons, and all these things that from the point of view of Lagrangians look like cool transformations and so on shell are just dead obvious because they're all the same thing, right? So you see, it's only the Lagrangian language that fools you into thinking there's this big fancy difference between the gauge fields and other things. They're all just massless bosons. So for massless particles, it's just bosons and fermions. Okay? Fancier situations, we can have anyons and so on, but in the most basic case, we have bosons and fermions. Okay? If we go all the way down to a 2 dimensions, 2 dimensions, there's nothing. There's no distinction even in bosons and fermions, which is true. Okay? So that's why you can bosonize things, and there is no fundamental distinction between any of these things. So 2 and 3 dimensions are too boring. 4 dimensions, though, the massless is U1, SO2, U1, and the massive is SO3, SU2. The 2 nicest Lie groups in the world, 1 abelian, 1 non-abelian, just perfect for the lazy theoretical physicist, okay, who still wants to be slightly cool, despite the fact, on top of the fact, of course, it's the space-time dimensionality of the real world. But never mind that. Yes, there's a couple of questions. Sorry, yes, you had the question first.
What if you were decomposing ridiculous to ask about a little group for space-like momentum?
No, it's not ridiculous. I don't remember what they are. Does anyone remember what they are? I presume they become Lorentzian, probably, but I don't remember what they are. Huh? Yeah, I would think it just changes the signature, but yeah. No, it's not ridiculous to ask what they are. Yeah.
Okay, but so I was just thinking, in your thing in 4 dimensions, the representations of the little groups and the massive particles are nice, right? The reason that the massive scale is so simple is because they're all symmetric tensors with indices. But
Yes.
did you think at all about what that would look like?
I think that would be the same. I mean, I think at that level, that's basically counting, and it doesn't really care about the signature. I think it's the same. I think it's basically the same. I think, yeah. Well, we could probably figure it out as we go along. But I'd be surprised if there's a significant difference. Probably what would change is the sort of reality properties of the. Yeah. I think. Well, okay. Well, let's see as we go along. I'm pretty sure it would be the same. The main reason there's a difference is just all this business about going to the origin, right? That's the reduction in the degrees of freedom from massless versus massive. That's why there's a difference between massless and massive. Otherwise, whenever the kind of basic degrees of freedom are the same, and I think there it would be if we changed time-like to a space-like. I doubt there's a significant difference.
What about SO0?
Huh? Right. So, yes. What about it? So. Scattering amplitudes for massless particles in 2 dimensions are notoriously ill-defined objects. So it's very likely this thing doesn't really make any sense at all. Okay, so already ordinary scattering amplitudes are not super well-defined even for massive objects. All the things that you're used to thinking about ordinary amplitudes, like we only care about the connected component of the S matrix because the particles come in, they hit each other, and they go back out. Well, that's not true in 1 + 1 dimensions because they keep hitting each other on the way in and out, right? So you can't just talk about the connected component of the scattering amplitudes. That's one thing. Of course, the other problem is if you have massless particles, you have long-range forces that are infinitely long-ranged in 1 + 1 in 1 + 1 dimensions. Right? An electric field doesn't die off at all, no matter how far out you go. So if you have any massless particles and they're coupled in any interesting way, the massless S matrices are just crap in 1 + 1 dimensions. So yes.
Talk about inclusive sections.
Yeah. So yes, you can talk about them, and so I'm uncomfortable with them, which doesn't mean that they don't make sense. But I'm not the person to ask about them. So. But anyway, we're sticking with d = 4. Yes. Yeah. Oh, sorry. You had a question too. Yes.
Yeah, so is there any meaning in the topology of SO? I mean, like,
oh yes. I'm ignoring all topological issues. So there's the usual topological business about double covers, and all of that is standard. But I'm only talking about the local issues here. Okay. So those topological issues are relevant. For example, when we say it's massless in SOD - 2, what tells me that it's half integrally quantized? And so for that, I need the standard topological arguments. But I'm not. I'm skipping that. Just, okay. So anyway, so this is just pure kinematics. So it means that a massive amplitude is, if it's massless, it's labeled by helicities. Now, what if it's massive? So if it's massive, we want to talk about things that transform under. We want to talk about things that transform under rotations, and here is the place where something utterly trivial kind of obstructs the standard way of thinking about massive. Something trivial at least gets in the way of thinking about amplitudes in a nice way, and makes you think before you start that massive amplitudes are going to be ugly, complicated objects. Okay, and what is the problem? Is just labeling the damn states. So you want to label the state. How do you label them? How do we normally label spin states when we teach spin to undergraduates? Right? We say that they're labeled by giving the value of the spin in the z direction. You give the total spin, and you give the spin in the z direction. Okay? So the way you label the states is by giving the total spin, which let's say we've given it, but then it's just by giving jz. Okay? And that's just gross to begin with, because just in our very labeling of the states, we are breaking rotational invariance. Okay? So that means that if you want to talk about scattering amplitudes, what? They have to carry this index along with them that says what the z component of the spin is. And so everything is going to have reference to this z component. And maybe for each particle, you can independently specify. Maybe there's a separate z component for everybody. But still, you're carrying around this reference object around with you everywhere you go, right? And so it doesn't seem as canonical or crisp or nice as the massless amplitudes that are naturally labeled by their helicity. So once you give the particle momenta, you don't have to give another reference direction to talk about what the spin is, right? So, okay. Now, this sounds like a kind of a dumb technicality, and it is a dumb technicality. Okay, so the way to deal with it is to just go back, and in fact, this is a useful thing just for, just even for thinking about SU2. I mean, just for thinking about even spin for undergraduates. Instead of labeling states by giving the z component of the angular momentum, we can think about states more invariantly as having some number of SU2 indices. So the sort of irony is that so the particle of spin s, a general state is specified by giving a 2s index symmetric tensor. Okay, with all indices symmetrized. Now the irony is that this way of talking about spin in terms of giving the maximal spin and then using lowering operators to go down and so on. This is the way we teach it to undergraduates. The irony is that this is actually a sophisticated way of thinking about spin, because this is the method that works for any Lie group. Okay, and that's the way you're supposed to think about the representations of any Lie group. And it makes no use of the special properties of SU2, where we have, or SUN in general, which get even simpler for SU2, where we use tensor analysis in the usual way that we like. So the way to label a state, is to give a 2s index symmetric tensor. So let's just do the accounting. So first let's just do some counting, and then we'll connect this to the usual way of thinking about. Spin states. So obviously, with one index, this has 2 degrees of freedom. With 2 indices, both downstairs, symmetrize. I have 2 times 3 over 2 equals 3 degrees of freedom. With 3 indices downstairs, I have 2 times 3 times 2, 4 over 2 times 3 is 4 degrees of freedom, and so on. So that's exactly the correct number of degrees of freedom for the particle of appropriate spin. By the way, if I think of the 2 indices here, let me just be a little intuitive about it here, then we'll say it formally in a moment. If I think about these, if I think about psi I, if I think about this I index as being like plus and minus, okay, then what does it mean to say it's 2-index symmetric tensor? It means that the only non-vanishing components, for example, for this case, the only non-vanishing components are psi plus plus plus, psi 2 pluses and a minus, 1 minus and 2 pluses, and all minus. Okay, and the fact that it's symmetrized means that you don't have to say where the location is. It's just specified by saying how many are plus and how many are minus, exactly as you would expect. And so this also tells you can think about this all plus component as being the top spin component, right? In a given direction. This is the next one down, the next one down, and the bottom spin component. Okay? Is that clear? So if you wanted to connect this literally to I mean, if someone hands you if someone hands you this state, and you want to know so given this state, psi I1 through I2s, let's say that I'm interested in a given direction n hat. I have the psi plus I and psi minus I. So these are the eigenstates of S dot. So this would be S dot n hat psi. And these depend on n hat. S dot n hat psi plus minus n hat is equal to plus minus psi plus minus of n hat. Okay. Then if I have a state psi in the conventional language, I want a state psi, and I want to see how does this state psi decompose into something in the direction n hat that has spin j. Then in this language, it's just a contraction of this psi I1 through I2s, and then I put zeta pluses n hat to the m plus, and zeta minus in the n hat direction to the m minus, with m plus minus m minus equals j, and of course m plus plus m minus equals 2s. Okay? So that's how we connect this is the usual way someone hands you a state, right? And so the components of this state are captured by this symmetric tensor, and this is the way you can go back and forth between the two languages. Okay, but this language is much nicer because it doesn't force you. So in this way of thinking about things, the choice of labeling the states and so on is done at the very end. You want to know what the amplitude is in a given direction. You take this symmetric tensor and you project it in those directions. Okay. But the object itself is just a simple, nice simple symmetric tensor. Okay, so that's how to think about SU2. Maybe I'll do a tiny example, just so you see that this thing has some nice content, and you'll learn something before 8 o'clock. How we can think about spherical harmonics. This is just standard undergraduate stuff. But how do we think about spherical harmonics? See, probably most of you, if I woke you up in the middle of the night and said, what's the seventh spherical harmonic, right? You'd probably not know how to do it, right? In principle how to do it. There's some L squared and blah, and there's some Laplacian, and it's very boring. It's very boring. Okay, so of course you're not going to remember it in the middle of the night, but this you'll remember in the middle of the night. I promise you. Okay, let's remember, what is the purpose? What are we supposed to do with spherical harmonics? What's the idea? The idea is that we want to build out of coordinates xi, so these transform like vectors under rotations. We'd like to build out of these coordinates things that are irreps under things with general number of indices that are irreps under SOD, right? But the problem is that for a vector everything is fine, but already for spin 2 I can talk about something that's xi xj, and I can also have something that's delta ij x squared, okay? And so x dot x, and I would like to figure out what linear combination of these things are the interesting ones. Okay, so I want to take out the traces. In this case, it's still easy to do. I know how to take out the trace part, right? So I have minus a third delta ij x squared, and now this thing is both symmetric and traceless. Okay. But as you go to higher and higher spins, there's just the annoyance of taking out the trace parts. Okay? There's just some so the question is there some and that's what the spherical harmonics are just all about. There's the polynomials in the x's that systematically take out the trace parts. But this is the nicer way of thinking about them. So you are familiar with the fact that we can take x and dot it with the Pauli matrices. So this gives us the famous z minus z, x minus iy, x plus iy. But in the language of what we're talking about, this is something which is in SU2, has SU2 indices with one upstairs and one downstairs index. Okay? And you know that's right because it transforms under SU2 by conjugation. Okay? So SU2 acts on it as u dagger xu. Okay? In this way of talking about things, X is a Hermitian matrix and it's traceless, right? As we see. So X is traceless. And again, that's why it's annoying. So as I multiply two X's, many X's, I have to make sure to take out traces. I'm still not doing that. But there's a closely related, but what should we do? We should work with all downstairs indices, right? That's the point, is that all downstairs, all we have to do is keep track of symmetric tensors, nothing else. So there's something where I just use the epsilon symbol to lower the SU2 index, and so I have x lower ij. Now what is this? This, if I write it as a matrix, is like, I don't know, minus x minus iy, z, z, and x plus iy. So this is a matrix you don't normally think about. It's a symmetric matrix, and it has no trace properties at all. Of course, it doesn't make sense to take the trace of this matrix. It has two downstairs indices. Okay? But it's symmetric. All right. So now, remember, what is the purpose in life? I'm trying to find some tensor that's made out of the x's. So let's say in spin 2x, there's some tensor, ti1, i2, up to i2s minus 1, i2s. I'm trying to find some tensor here made out of the x's that's just totally symmetric. Now, that's it, right? Because now there's no issue of making them traceless anymore. So I want to make them out of the x's. Because it's totally symmetric, in order to tell you what this tensor is, it suffices to just dot it with a generic vector. So if I choose some random xi, if I give you this information, I've given you everything, right? Because so that's what I want, is to get some function of the x's, which I make out of these x's, and it's totally symmetric. Well, but in this way of saying it, it's obvious what it is. What could this possibly be? This is just equal to xi x, just xi, cj, xij to the power of s. That's it. Okay. And so those are the spherical harmonics. So you see, you just write xi as some general alpha beta. Okay? And so if I compute what is xi I, xj, xij, this is equal to, in terms of these variables, it's equal to minus x minus iy alpha squared plus 2 alpha beta z plus x plus iy beta squared. Okay? If I make x a unit vector, just to make things a little bit more compact, this is equal to minus e to the negative I phi sine theta alpha squared plus 2 alpha beta cos theta plus e to the plus I phi beta squared sine theta. Okay, so this is what xc is. And therefore, the symmetric tensor is what I get by just taking that object minus negative e to the I phi sine theta alpha squared plus 2 alpha beta cos theta plus e to the plus I phi sine theta beta squared to the power of s. And this expands as a sum over alpha to the m plus, beta to the m minus, well, alpha to the j, beta to the s minus 2j, yj of theta and phi. Those are the spherical harmonics. Okay? So that's how you can remember it. The spherical harmonics are just the s power of that xx xeta of the. So everything about the spherical harmonic is to write that matrix down with the two lower indices. Okay? So that's actually useful, and you can remember what it is in the middle of the night, and also derive the generating function for it, everything. So the way, just to remember the middle of the night is, it's just the X matrix sandwiched between two vectors raised to the S power. Okay, so this is just total triviality, SU2 group theory as described by symmetric tensors. Okay, symmetric rank 2s tensors. Any questions about this? How many people have seen this discussion of spherical harmonics before? Yeah, it's shockingly underrepresented in undergraduate courses. This is the way it should be done. I mean, it's much simpler than the standard presentations. Okay, so now we know what the labels are, right? For oh, by the way, I'll leave it as an exercise for you. You can also use this to find trivially the rotation matrix for total general spin. Okay, so you want to do a rotation for spin 17 by angle, by angle cos theta. What is that 17 by 17 matrix? It's completely trivial to, or whatever, the 35 by 35 matrix. It's totally trivial using this formalism to work it out. So everything about SU2 group theory is totally straightforward in this language. Okay, so now we know what it is that we're after. So just to do an example, let's say I have a massless particle of helicity -2, a massive particle of spin 1, so 2 massive and spin 1, and I don't know, a third scalar particle of spin 0, massless, and a fourth massive particle of spin 2. Then, if we're going to talk about the scattering amplitude for an object like this, then already just by kinematics, we know what we're after, right? So this has to be some function. This is some function that has to depend on the momenta P1, P2, P3, and P4. And furthermore, it needs to have the property that well, actually, yeah. Let me wait just for a moment. Let me wait just for a moment before doing this, just so we do something. We do a little more. Anyway, so we know what the little groups are. We know for U1 it's just trivial. It's phases. There's nothing to do. But for SU2 we're going to label them by symmetric tensors. Okay, so now comes the heart of the matter, which is how do we actually represent scattering amplitudes that have these properties? And let me remind you of the standard. Approach, the standard textbook approach to this problem. The standard textbook approach is to say that, let's say we have massless spin 1 particles. the standard textbook approach is to calculate a Feynman amplitude, right? So it's not really an amplitude, it's a tensor. And to get the actual amplitudes that we care about by introducing the notion of a polarization vector. So if you have some given helicity for particle 1, we dot it with its corresponding polarization vector. Okay, so we dot this with polarization vector P1. Okay, and the polarization depends on helicity. And if it's a massive particle, then we should dot it with some epsilon mu that now has a little group index. In this case, there would be some ij that corresponds to the, in the language that we want, that would correspond to the SU2 spin components. Actually, even in the standard textbooks, people don't, because they don't use this representation so explicitly, they don't write it like this. They'll just say you dot it with some polarization vector that encodes what you think the spin is. But if we want to do it this way, we would have to imagine that this is an object that has a Lorentz index and has little group indices on the other side, right? Because that's the whole point. Is that the amplitudes are things that are functions of momenta that are acted on by Lorentz transformations, but they have to also have little group indices because they have to pick up little group factors after you do the Lorentz transformations. Okay? And now, there are a number of problems with describing things in this way. The most famous ones are with the massless spin 1 particles, right? Which are, famously have the gauge redundancy problem. There is no such thing as uniquely defined polarization vectors for a given helicity. Okay? And you know this because there's only 2 spin degrees of freedom for a massless spin 1 particle, and there's no Lorentz invariant way of imposing conditions on a 4 vector to get you down to 2 degrees of freedom. Okay? So I can say that I have epsilon mu that has 4 degrees of freedom and demand that p mu epsilon mu is 0, but then I'm stuck. I still have to somehow get rid of 1 degree of freedom. And probably most of you are experts on this and know it, but just to stress the point, let's say you say, screw you. This is what I mean by polarization vectors. Why are you bothering me? I know there's something that looks like this. The particle is moving in the z direction, and there's even an I here and everything. So those are what the helicity states are. What's wrong with that? What's wrong with that? Does anyone know what's wrong with that?
Breaks Lorentz invariance.
Yeah, it breaks Lorentz invariance. Just because you put a slop mu index on something doesn't make it Lorentz invariant. Okay, so this is an important lesson. Okay, and the problem is that if you do a Lorentz transformation on this guy, well, if you do a Lorentz transformation on this, which is just a rotation around the z-axis, it's not Lorentz invariant. It shouldn't be invariant. It picks up a phase, which is good, right? But the problem is that you can do another thing. You can do a boost. And you can do a boost in the x direction and a rotation. Yeah, sorry. So we boost. Yeah, sorry. You do a boost in this direction. You rotate a little. You boost back and you rotate back. Okay. So that combination of steps is something that takes you from the momentum back to itself, but it will not bring this polarization vector back to this form. Okay? And the problem is that those zeros there don't mean anything. There's no Lorentz invariant way of making those zeros mean something. So these are not Lorentz invariant. The only thing we can do is declare, of course, it'll come back to itself up to, so if lambda p equals p, then epsilon will come back to itself plus something proportional to p. Okay, so that's the famous reason why we can say that we have epsilon dot p equals 0 and define this equivalence class of epsilon such that epsilon is identified with anything proportional to p, right? So this gauge equivalence class is the thing which is Lorentz invariant. But then that means you have to work very hard to make sure the theory is such that when you dot it with either epsilon or epsilon plus anything times p, you get the same answer. Okay, so that's a famous and familiar reason why it's difficult why polarization vectors are kind of don't allow. They force you to use a redundant description to talk about the physics. Perfectly correct, you can do it, but that's the price you have to pay. But even for massive particles, we have a similar problem. For example, even let's talk about massive. Massive spin 1. Okay. Well, we still have these polarization vectors epsilon mu, and we still have to impose these things like epsilon dot p equals 0. Right? We don't have this. We don't have the gauge freedom, but we still have epsilon dot p equals 0. Or it's even worse for spin 1/2. Let's say you have a massive spin 1/2 particle. Then these things that we carry on the outside are Dirac spinners, and so those polarization vectors have to satisfy the Dirac equation, right? So they're constrained. Even these massive objects are constrained. Why are they constrained? So where does this epsilon dot p equals 0 come from for a massive particle? Of course, we need it to cut down the degrees of freedom, but that is, in the purest form, is showing you that you're building your objects out of fields and not particles. Those are the equations of motion for the fields that put them on shell. Right? Epsilon dot p equals 0 together with p squared equals m squared is the equation of motion for massive spin 1. For the field that puts it on shell. Similarly, the Dirac equation, it may have bothered you when you were learning field theory that you're dragging 4 components around with you everywhere you go, even though the damn object has 2 spin degrees of freedom. Why do you have to do that? Right? It's because of fields, because quantum fields demand you to carry these 4 objects around and get rid of 2 of them when you put them on shell, when you dot into things on the outside. So both for massless and massive, the situation is not ideal. And so what we'd like to do is find good variables that make the little group properties as manifest as possible. And that's what the spin helicity variables are all about. So normally spin helicity variables are presented as kind of a trick for representing momenta. But it's not a trick. So we know that we have these p alpha alpha dots. We know that, let's say the particles are massless. We know the determinant of p is 0, so we can write this as lambda alpha lambda tilde alpha dot. But that's not the conceptually most important part, the fact that we can write it that way. What's much more important is that this allows us, that it not just allows us, but these lambdas carry precisely the little group transformation properties that the amplitudes do. Okay, and this is kind of a trivial point, but if you haven't thought about it, let me just say it quickly, and you should go home in your closets and think about it now, or later tonight, because you see, there's an ambiguity in what the lambdas and lambda tildes mean. We can rescale them and keep p fixed. That ambiguity smells a lot like the little group, and in fact it's precisely the little group. You see this if you go through exactly the same steps. How would I fix the ambiguity and what I mean by lambda? Let's say I want to, on the computer, I want to tell Mathematica what are the lambdas and lambda tildes for any momenta. So how would I do it? I would first fix some momentum, some k. For that k, I would write it as lambda alpha of k, lambda tilde alpha dot of k by making a choice. It's not unique. I make a choice. So for example, I choose k alpha alpha dot to be 2e 0 0 0 for a particle moving in the z direction, and I choose lambda alpha k to be root 2e 1 0, and lambda tilde k alpha dot to be root 2e 1 0. And the choice that I made is not to put some phase here to cancel on the other side and so on. I've made a choice and I'm done, right? Now everything is parallel. Now I define what I mean by lambda for some p as a particular Lorentz transformation, L alpha beta that depends on p, for what I meant by lambda for k. All right? And after having done that, now I can ask the question, what does lambda look like after I do a Lorentz transformation on p? And the answer is not. It does not look like L alpha beta lambda beta of p. Okay? Just like with the story of the little group. But it is equal to that up to a phase, e to the I theta, that depends on the, sorry, here I'm doing a general Lorentz transformation, some lambda. Okay? So a theta that depends on lambda and p, on lambda alpha beta, lambda beta of p. Again, most obviously, just think about a particle moving, just something moving in the z direction and just doing a rotation around the z direction. You have to pick up a phase. Okay? But the construction is exactly the same as the story of the little group, and this phase is exactly the phase associated with the little group. Okay? This is important. Normally when we talk about amplitudes, we're a little bit loose about this. We say, oh, the amplitudes transform with some phase, and that reflects the helicity. But it's not some phase under Lorentz transformations. It's a very particular phase that it has to pick up. And it does pick up exactly that particular phase. I mean, that's the particular phase of the actual little group. And just as a shortcut for making sure that this happens, it's enough for us to check that it has the correct homogeneities under general rescalings. But the actual rescalings that you get are not independent. They come, you do a particular Lorentz transformation, you pick up particular phases. Okay? Okay, so that's the story for massless amplitudes, and as you know very well, so that's what's conceptually important about them, is that now we finally, with the spinor helicity variables, we know how to represent amplitudes, so the little group is manifest. So if I have the helicities and lambdas and lambda tildes, now all the information about the helicities is contained in the famous statement that I should pick up this TA to the minus 2h m of lambda and lambda tilde. Okay? So now finally we can ask what the analog of this is for massive particles. All right. So, when we have a massive particle, we have p squared equals m squared. And therefore, the determinant of the p matrix is equal to m squared. Okay, so we'll keep that in mind. So that means that the p matrix has rank 2. And so I can write p alpha alpha dot as some lambda alpha dot tilde alpha dot 1 plus lambda alpha is rank 2, lambda tilde alpha dot 2. Okay, so it's a sum of two things that look like that, just trivially. But of course, I can write this as p alpha alpha dot is lambda alpha some index I, lambda tilde alpha dot with a lower index I, or with an upper index I contracting with the epsilon symbol. It doesn't make any difference. And now this index I runs from 1 to 2, and it's exactly the little group. Say by precisely the same logic as we had before. Okay? So once again, I can't uniquely specify a lambda associated with a p, blah, blah, blah. And so when I do a transformation on the lambdas, I pick up an SU2 transformation on these indices. Okay? So those are the little group indices. And so let's if I look at the determinant of p, or if I just epsilon the p's together, this is equal to the determinant of lambda. So the lambdas epsilon together times the determinant of lambda tilde. Okay? So this is literally, this you would think of as lambda alpha I, lambda beta j, like epsilon ij, for example, epsilon alpha beta. So that's what I mean by that determinant, as usual. And so I learn, too, that det lambda that lambda tilde is equal to m squared. Okay? So now there's a little choice to make. So we could write that lambda is equal to some sort of capital M, that lambda tilde equals capital M tilde. And that's the kind of thing that you're tempted to do because you know that it's good to keep, anyway, this is perfectly fine, but m and m tilde would have to satisfy the constraint that m tilde is equal to m squared. Okay? I don't lose anything by, at the moment anyway, by just setting m equals m tilde equals m. Okay, and if I do that, that lambda and that lambda tilde are equal, are set equal to each other. So, what are these choices doing? So, you'll notice that I still seem to have the freedom. I still seem to have the freedom in rescaling lambda and lambda tilde. Okay? I can rephase lambda and lambda tilde, or rescale them keeping in the usual way with the t and the t inverse. So there's like a GL1 part of this guy. Okay? But that GL1 is precisely carried by m and m tilde. Okay? So if I wanted to keep that GL1, that's like keeping m and m tilde independent such that only the product is fixed. But the ratio m over m tilde transforms under that GL1. So this GL1 doesn't actually have any content. If you give me anything, any expression, I can multiply by appropriate powers of m over m tilde to make it GL1 invariant. Okay? And so I'm fixing that GL1. Another way of saying this is I can fix that GL1 redundancy just by demanding that m equals m tilde equals m. Then the GL1 is gone. Okay? Notice I couldn't do that in the massless limit. Okay? But when the particle is massive, I can fix this GL1 just by demanding m equals m tilde. Okay? This is quite important. This seems like a little technical point, but it's very important. We'll see why it's important when we well, it's important all over the place. But now we have all the tools at our disposal. Okay? Because now what is a scattering amplitude? Kinematically, a scattering amplitude is a function of lambdas and lambda tildes. So a scattering amplitude is a function of lambdas and lambda tildes for massive particles. These things with indices, whether we put them upstairs or downstairs doesn't make any difference. We can put them all upstairs if we want for massive particles. And it needs to be such that for each massive particle, it's actually a tensor of rank 2s in that appropriate index. It has to have 2s symmetric indices for a particle of spin s. So let's do an example. So what is this? Let's just write something down. So let's say I have 1 I2 1, actually let me do 1J3, I don't know. This is pretty random, but so what is this? Okay.
So why does 2 on the left doesn't have any index?
Good, because 2 is massless. Okay, so this is going to be some funny, oh, sorry, this is a different 2. So, yeah, so, yes, 1, 2, 3, and I just want to have, okay, let's do 3, 4. That's stupid too. I shouldn't just invent these things off. Let's just leave it at that. No, let's not leave it at that. Huh? You want to make 4 massive? All right, let's make 4 massive. Why not? So let's do 3, 4. Are you happy now? All right. Good. Okay. Now, and remember, whatever I do, I have to make a symmetrized. It's got to be a symmetric tensor. So I'm always symmetrizing in these indices. Okay. So what does this correspond to? This is something that is an amplitude for a particle where particle 1 has spin 1. Particle 2 is a fermion of helicity -1, massless. Particle 3 is a massless spin 1, also with helicity -1. And particle 4 is massive with, it's just with spin 1/2 and massive. Okay? So, all right. Now, but what I wanted to illustrate is the following. Let me now add something to this. Let's see. What should I do? So let's say I do, I don't know, 1I4K. Yes, 1I. Yeah, 1J 2. So I got rid of 4. I have 2. Sorry, let me do 1J3 and 2,3. There we go. Okay? Now, here's another expression, which as far as the helicities for 3, the weights for 3 and 2 go, everything looks cool. Everything looks fine, right? However, if you're a normal massless guy, you would think this looks like very wrong and bad for particles 1 and 4, right? Because I'm adding angle brackets and square brackets, and everything looks like a mess, okay? But this is completely legal. This is 100% legal here, precisely because we don't have the GL1 for the massive spinor variables, okay? So I'm allowed to add them. There's no weight requirement on the massive spinor helicity variables, okay? In other words, I only have to make sure that there's symmetric spin 2s tensor in their own variable, and that's it. I don't have to do anything after that. Okay, is that clear? Okay, so now this is important for a whole variety of reasons, but let's keep going a little bit, and you'll see an application in a moment. Now, at the moment, this all seems perfectly fine, but just notationally, it does seem a little cumbersome to drag around all these indices all the time, especially as the spins get large. You know, you're cluttering your page with all these indices everywhere, symmetrized indices everywhere, and so on. Fortunately, we don't need to keep them. It's really stupid to write them down all the time, because we're just symmetrizing them anyway. Okay? So here's what you do. You just don't write the indices down. Okay? But you keep track of whether the particles are massive or massless. That's very important. So if you're doing it in tech, you write them in bold. If you're doing them on a blackboard, you underline them or something. You just have to remember who's massive and massless. So if we do that, well, then this is just, then this looks slightly simpler. but I just have 1, 2, 1, 3. Right? I'm just doing trivial stuff here. 3, 4 plus 1, 4, 1, 3, 2, 3. Okay, so this is some putative massive amplitudes for this funny process. Okay?
So when you do like that, you just always assume that you symmetrize over.
Because that's what you're doing. Yes, that's right. So that's why you don't need to write it down, because you're going to symmetrize anyway. Okay? So then there's no point in continuing, in always writing them down. Right. All right. Any questions about this so far? Yes.
The frequent amplitude unique? Or?
We can talk about all that after we're breaking. Yes.
We have break. We already have coffee.
Oh, okay, great. Okay, yeah, this is a good place to a break. All right.